Let's take a moment to consider something known as a phase diagram. A phase diagram is something that plots pressure versus temperature data for a particular substance to indicate what physical state the substance will be in given that pressure and temperature combination. It tells us whether at that pressure-temperature combination the substance is going to be a solid, a liquid, or a gas. This would be what a fairly typical phase diagram would look like. Now let's consider for a moment what we may find in the three areas of the phase diagram. If we have a fairly high temperature as temperature goes up, but the pressure is fairly low, meaning the particles are allowed to spread out, that would allow something to be in the gas phase. So this region of the phase diagram would indicate something as gaseous. Now if we were to increase, say we are at a temperature right here, and we increase the pressure, the gaseous particles start to get squeezed together. By increasing the pressure, essentially what we're doing is squishing the particles closer and closer together. As gaseous particles get squeezed tight enough together, their attractive forces will come into play, and what will happen is the gas will eventually turn into the liquid phase. Which would mean that this area, when we go up to a higher pressure at a constant temperature, this would be the area where we would find the liquid phase for a particular material. If we're in the area of the liquid phase and all we do is cool something at a constant pressure to a lower temperature, what's going to happen is the motion of the particles slows down, and this would cause something to go from liquid to a solid phase state. So this area of our phase diagram, we'd find a material in the solid phase. The information the diagram now provides us is under what pressure and temperature conditions would a material be a solid, a liquid, a gas, and under what pressure and temperature combinations does something go through a phase change. For example, if we extend out here, this is our pressure reading, and this is our temperature reading that we have. If our data point falls in this area, that would indicate that under those conditions, the material under that pressure and temperature combination, this material would exist as a solid. If we change our pressure and temperature combination, and say we come out here for this temperature, and it's at this particular pressure, that would indicate that under these conditions, this material under that pressure-temperature combination would be in the gas phase. Change our pressure and temperature combination again, so that our pressure, say, brings us over to here. At this particular temperature, this data point would indicate under that pressure-temperature combination, this particular material would exist in the liquid state. If a data point falls on one of the lines in our phase diagram, say we fall out here right on the liquid to gas change, that would indicate that under this pressure-temperature combination, we are going through a liquid to gas, or we could look at it as a gas going back to liquid phase change. This particular temperature would be something at that pressure. This would be a boiling point for this particular material. Could also look at it as if we go from gas to liquid, it could be looked at as also the point when condensation takes place. And it's actually a point of equilibrium, that when we fall on one of the lines dividing the phases, at that particular condition, it would be an equilibrium scenario between liquid and gas and liquid, which is actually what's taking place when something boils or when something condenses. If a data point falls along here, right on the line between solid and gas, this would actually be something that's referred to as sublimation. Something going directly from the solid phase to the gas phase would be subliming. Something you may be familiar with that does this is dry ice. A block of dry ice, which is solid CO2, at room pressure and room temperature will go directly to CO2 that's in the gas phase, which would be the process of sublimation. If we reverse that process and go from a gas directly to a solid, that process is known as deposition. Either way, when we fall on this line between solid and gas, it's a phase change is taking place, and we'd be in an equilibrium between gas phase and solid phase at that particular pressure and temperature combination. If the phase change happens to fall directly here between solid and liquid, that would be an area where under this pressure temperature combination the process of melting would be taking place when we go from solid to liquid, and in reverse when we go from liquid back to solid, that would be freezing. Freezing and melting, it's the same temperature pressure combination, and we'd be in equilibrium at that point when this phase change is taking place. In the circumstance where the pressure and temperature brings us right to the point where all three lines intersect, this is something known on phase diagrams as the triple point. And it's a rather unique circumstance in that at the triple point, all three phases are in equilibrium. So at the conditions of the triple point, we would have solid, liquid, and gas phases all existing simultaneously and all in a state of equilibrium with one another. Another point of interest on a phase diagram, if you'll notice the line here between liquid and gas terminates. It has a dead end. This point out here that lines up with this temperature, that's something that's known as the critical temperature. Now the critical temperature, what this tells us is that beyond this temperature, once we go above here, if you'll notice, there's no liquid phase that exists on the diagram. That's because beyond this temperature, there's enough energy present in the material that no matter what we do with it to pressurize it, we cannot cause it to go from the gas to the liquid phase. So above the critical temperature, the material can only exist in the gas phase. Below the critical temperature, a gas could be pressurized to make it turn into the liquid phase, even at a fairly high temperature. Now, other information we can get from a phase diagram is we can find out things such as boiling point, normal boiling point, freezing point, etc. Boiling point is when we're at equilibrium between the liquid and the gas phase. Whatever temperature and pressure conditions cause the liquid to turn into gas and gas to return to liquid would be considered a boiling point. There's also a more specific boiling point, which is known as the normal boiling point. The normal boiling point would be when we have conditions considered normal for sea level, which would be a pressure of 1 atmosphere, similar to what we have in Darien, Illinois. If we extend from 1 atmosphere over to the gas-liquid phase change right here on our diagram, this temperature, when the gas-liquid phase change is taking place, this particular temperature under 1 atmosphere conditions would be known as the normal boiling point for whatever material we're taking a look at. Now, once again, what a normal boiling point is, it's the temperature that we have when the liquid to gas phase change is taking place at specifically 1 atmosphere of outside pressure. That's considered a normal boiling point. Now, a particular liquid can have a number of different boiling points. Boiling point is merely when we have the pressure and temperature conditions to cause a gas and liquid equilibrium to exist as we're going through a phase change between the liquid and gas phases. Normal boiling point is specifically at 1 atmosphere. Now, if we change the outside pressure to something other than 1 atmosphere, we can still have a liquid to gas phase change. For example, on this new combination, we've changed the pressure that's over the liquid to 0.8 atmospheres, and we have a new temperature at which the gas-liquid phase change takes place. This would be considered a boiling point. It's just not the normal boiling point. This would be why, for example, water on a mountaintop where the outside pressure is much less than 1 atmosphere will boil at a lower temperature than it will under standard or normal conditions of 1 atmosphere. So a boiling point is liquid to gas phase change at any pressure temperature combination. The normal boiling point is the liquid to gas phase change occurring specifically at 1 atmosphere pressure. The same would be true for a phase change to a solid to liquid, which is the freezing and melting point. That would take place over here between our solid and liquid phases. This point, because it's not at 1 atmosphere pressure, would be considered just any old freezing and melting point, whereas if we go specifically at 1 atmosphere pressure, the temperature we'd have for that specific freezing or melting point would be known as the normal freezing and melting point. The shape of a phase diagram can also give us information about the density of solid and liquid phases. For most materials, the solid is more dense than the liquid, in that in a solid the particles are more closely packed together than in a liquid. However, in some rare circumstances, the liquid is actually more dense than the solid. A phase diagram can tell us which circumstance exists for a particular material. Let's take a look at the left phase diagram. We'll pick a temperature right here, and what we're going to do is increase the pressure at a constant temperature. And on this one, as we can see, as we increase the pressure at a constant temperature, we go from the gas directly to the solid phase, and then no matter how much we increase the pressure, we remain in the solid phase. This would be indicative of where the solid has a greater density than the liquid phase, which is typical of most materials. If we look at the right diagram, on the other hand, once again pick a temperature, and we're going to increase the pressure at a constant temperature, and we can see we cross here from the gas and we go to the solid phase. As the material, the particles are getting packed very closely together. As we increase the pressure, though, we can see as the particles get packed even closer together, which would be an increase in density, we actually go from the solid to the liquid phase. So in this circumstance, when we see this phase line angling off to the left between solid and liquid, that would tell us that this material, the liquid, is more dense than the solid. Even though this circumstance is fairly rare, a common material we're all familiar with has the circumstance where the solid is actually less dense than the liquid. This would be true for water. Picture ice cubes. Ice cubes in a glass of water will float, indicating that the solid is less dense than the liquid, or another way to say this is the liquid would be more dense than the solid. So this particular type of graph that we have here on the right would be representative of something such as water, where the liquid is more dense than the solid. The graph on the left side is much more typical, and that would show us that the solid is more dense than the liquid. Now once again, what tells us which material is more dense is we pick a temperature, increase the pressure at a constant temperature, and we'll see that as we increase pressure at a constant temperature, in this first diagram on the left, we merely go from the gas to the solid phase. It never goes back to liquid. This tells us when it's most closely packed under high pressure, the solid is more dense than the liquid. In our diagram on the right, once again picking a temperature and keeping the temperature constant but increasing the pressure, we can see as the pressure gets greater and greater, we actually go from gas to solid, and the solid, interesting, will change to a liquid as we increase pressure. At the higher pressure, when the particles are closer together, that would be a more dense state. So in this diagram on the right, it would indicate that the liquid is more dense than the solid.